In this video, we're going to be taking a look at diagnosing fan or blower motors, basically smaller PSC motors. PSC motors, capacitor, start, run, and common. So I titled this presentation or this video, When Motors Don't Fail. And the reason I did so is because a lot of times those of us on the HVAC forensics side, in other words, we're going out and doing a secondary inspection after another tech has been there to figure out what actually failed. We a lot of times find things that should have been diagnosed correctly the first time, and a lot of times it's because somebody didn't know better. So I'm going to talk about a motor in this presentation that I looked at probably sometime last week and diagnosed it the second time. So let's walk through. Okay, the motor in question had been removed prior to my arrival. It was replaced to provide emergency cooling, and the customer was told the equipment was too old to repair and the new system is partially installed already. In other words, the new condenser is there. The air handler is still sitting, hasn't been installed. So the new condenser was installed on the old air handler. The parts were left for me, okay? So the motor in question was actually removed, left for me next to the old condenser. So what we have is we have all our windings, we have a motor, we have a capacitor, so everything is there. We have a nameplate that's showing me what the motor windings are, okay? And so we have two brown wires on the capacitor. We have a purple or blue winding. We have our black and our red for low and high. Okay, so there we can see basically how things come together. Okay, the capacitor is supposed to be, and the reason I'm showing this is most motor labels do have a capacitor on it. Tells us what capacitor needs to be in there. This is a GE motor. They're pretty good about it. It's a 1075 230 volt motor. Okay, first thing I did was, even though I can't show it on still pictures, I did go ahead and spin the motor. It spins freely. Nothing wrong with the mounting, nothing burnt looking. The shaft is in actually good shape. Bearings are good. So mechanically, we're fine. Okay, take a ohm reading from start to run, and I'll show you this on a diagram in a minute why I do it in this way. So I'm going to go from start to run. I got 36.5 ohms. Okay, important number to remember. So again, start to run, 36.5 ohms. Okay, take another reading. We go from start to common. Okay, we get 29.1. Take another reading, run to common. We get 7.6. Now there's some magic numbers in these readings, okay? So again, if I go back, we got 36.5, okay, across from start to run. We got 29.1 from start to common. We got 7.6 from run to common. Notice the last two numbers, the 29.1 and the 7.6, add up to 36.7. Okay, so the first reading we took was start to run, 36.5. The next two readings added up to 36.7. 0.2 ohm difference between that. Okay, so what we have actually done, when I took the start to run reading, I came across and have both these coils. The run was 7.6. The start to common was 29.1. And when you take this together, what you have proven is that the windings are properly connected and intact in the blower motor. Okay? Because run to common, start to common, so we know our terminals here are good. Okay, we know our common terminal is good, so we know this isn't broken here. And then when we go here, we know we've proven that this connection is good. Okay, so that's a PSC motor diagram. So it takes 3 ohm readings to prove that your windings are connected properly. Now, The next set of readings that is very important to take is all of these terminals to frame ground. Okay, in other words, to the ground or the frame of the motor. Why do I do this? It's to make sure that these windings have not shorted to the motor itself, to the frame. Okay, so we go from start to ground. We have OL. That just tells me there's no continuity. We have common to ground. That tells me there's no continuity between that winding or that connection and ground. We have run to ground. Again, OL. We have no continuity between the motor and the frame. Why is this important? It tells me that the motor windings are not damaged. So between 6 readings, I can tell you that the motor is not electrically damaged. We can also go back and say, okay, the motor spins freely. Okay, so we don't have damage to the bearings or anything else like that. So electronically and mechanically, this motor's so good. So the question is, why did it fail? What's failed? So we have one more component we have to look at to determine what caused this motor to fail. Take a reading across both terminals of the capacitor. Okay, we come up with 0 microfarads. Okay, the capacitor is shorted. So what was going on is this motor wasn't running because the capacitor was shorted. Okay, perfect short on this capacitor. Okay, capacitor is not bulged. It's not damaged in any way. The capacitor just died. Okay, so what's the right thing to do here for this customer? Well, that's an ethical decision. That's really up to you. In the case of this technician, he chose to replace the entire equipment. Okay, there's more to it, but that will be for another presentation. But the bottom line is that this motor had a bad capacitor.